Have you ever wondered why you can dip your toes in the Red Sea and it feels like a warm bath pretty much any time of year, but then a swim off the coast of California is, well, let's just say it's bracingly cold? It's not just about sunshine. No, there's a very specific recipe at work, a perfect storm of geography and physics that creates these permanently warm seas. Okay, let's get into it.
So, what's the secret sauce here? Why are some places, like the Persian Gulf or the Caribbean, just so consistently warm, while other spots are all over the place or just plain chilly? That is the big question we're digging into. Think of this as a quest to find the exact ingredients that cook up these amazing marine environments.
And this is a perfect way to see it. It's a tale of two coasts. On one side, you've got the Red Sea. It's narrow, it's hugged by desert, and it's almost completely locked in. It's a master at holding on to heat. Then you have the California coast, which is totally open to the huge Pacific Ocean, where deep, cold water is constantly getting pulled up to the surface. I mean, these are two places with completely different thermal stories.
All right, ingredient number one. This is the obvious one, right? The sun. Seas in these tropical and subtropical spots get absolutely blasted with intense sunlight all year round. This is the power source, the raw heat that's just pouring into the system day in and day out. It's the foundation for the whole recipe.
But here's the catch. If it was only about sunshine, then the entire tropical part of the world would have these super hot oceans, and we know that's just not how it works. This is where it gets really interesting. The sun provides the energy, for sure, but other factors decide whether that heat actually sticks around. So what else do you need?
So let's talk about ingredient number two. And honestly, this might be the most important one, the container itself. The actual shape of the land and the seafloor is absolutely critical. In these warm sea areas, the geography literally creates a trap that just locks all that heat in. And this quote just nails it. You should think of it like a natural greenhouse. All that solar energy gets in super easily and warms up the water. But because of the basin's unique shape and its very limited connection to the open ocean, that heat has nowhere to go. It can't mix with colder, deeper water, so it just builds up and up and up. You know, to really understand what these heat traps have, it's just as important to understand what they're missing. And what they're missing is a process called upwelling. This is basically the ocean's natural air conditioning system. It's where frigid, nutrient-packed water from the deep gets pulled to the surface. Places like the California coast have tons of upwelling, and that's what keeps them cool. Our warm seas, they're practically built to stop this from happening.
So how do you build one of these natural ovens? The recipe is right here. First, you need a shape that's mostly closed off, like the Red Sea or the Persian Gulf. Second, you connect it to the big ocean with a tiny little channel, like the Bab el-Mandeb Strait. This acts like a serious bottleneck, and it severely limits how much cool water can even get in. And the result? A system that is brilliant at trapping heat.
And just look at the payoff. Over 34 degrees Celsius, that's a staggering 93 degrees Fahrenheit. That's the surface temperature of the Red Sea in the summer. It is one of the warmest seas on the entire globe, and it's a direct result of this incredibly efficient heat-trapping geography.
Okay, so we've got our sun and we've got our heat trap, but we're not done yet. There's a final set of ingredients. Let's call them the reinforcers. These are the spices that take an already warm system and just crank the thermostat all the way up to 11, locking in that warmth for good. So let's break this down. First up, high salinity. In places like the Red Sea, there's a ton of evaporation, which makes the water extra salty. Salty water is denser, so it sinks, and it takes heat down with it, mixing it deep into the water. Then you have things like high-pressure zones in the atmosphere that basically act like cloud shields, guaranteeing maximum sun. And finally, you've got the big guns, warm currents that are like a conveyor belt of heat from other places, and trade winds that literally pile up all the warm surface water. Each one of these just adds another layer to the warmth. So there we have it, a recipe for a permanently warm sea. But let's zoom out for a second. Why does any of this matter beyond being a really cool science puzzle? Well, it turns out these unique places have a massive impact on everything from their local ecosystems all the way up to global climate patterns.
Yeah, these warm seas are not just isolated curiosities. They're the engines that power some of our planet's most incredible ecosystems, like coral reefs. They can influence weather thousands of miles away. They have a role in how the ocean absorbs carbon. And maybe most importantly right now, they are on the absolute front lines of a warming planet.
This chart really drives that point home. The very things that make these seas so good at trapping heat, their enclosed geography, also make them incredibly vulnerable. You can see it right here. These semi-enclosed seas are warming up way faster than the global open ocean. That heat trap is working overtime, and these areas are becoming critical hotspots for us to understand the real impacts of climate change.
And that leaves us with this final and frankly pretty urgent question. These environments are already pushing the limits of what a lot of marine life can handle. So as we keep adding more heat to the global system, what happens when nature's warmest places reach their breaking point? That's something scientists, and really all of us, need to figure out, and fast.